Okay, we've got ourselves here a rational function where the degree of the top is exactly one more than the degree of the bottom. Second degree on top, first degree on the bottom. So we're going to have ourselves a slant or oblique asymptote. Okay, let's first find the domain here. So remember, with rational functions, we find the domain. First, we factor top and bottom, see if anything cancels. That top may factor. Nothing's clearly nothing's going to cancel here, but let's see if we can factor this. So I think we want a 2x here and an x, and it looks like a -1 and a +1. That'll give us +2 -1, which is +1. Nothing's going to cancel out. If anything canceled, we would just have a hole, and we wouldn't have a vertical asymptote at the guy that causes problems in the bottom, the excluded value. Okay, so domain set the bottom not equal to 0 and solve. So x is not allowed to be 4, which makes our domain -infinity to 4 union 4 to infinity. That also means we have a vertical asymptote. Remember, vertical asymptotes are vertical lines at x equals 4. We will not have a horizontal asymptote. We only have a horizontal asymptote when the bottom in degree is less than or equal to the top. Here, the top's bigger. So now let's find that oblique, also known as a slant asymptote. And we do that using long division. So we're going to take the bottom into the top. Okay, so let's see. X goes into 2x squared, 2x times. We distribute 2x squared minus 8x. 2 times -4. Draw the line, change the signs. These cancel out. And we get 7x minus 1. And I can go one more time here. Plus 7. Distribute. 7x minus 28. Draw the line, change the signs. Those better cancel out. And what do we get? 27. So we get plus 27 over x minus 4. So that means this original fraction, h of x, could be written as 2x plus 7 times x minus 4 plus that remainder. No, sorry, that means the divisor here, the dividend, could be written as that. What we want is the original function. This guy divided by that guy could be written as 2x plus 7 plus 27 over x minus 4. And that's an ugly 7 there. Now, what do we care about? Why do we do that? Because what we're looking at here for any type of horizontal or slant asymptote is end behavior. What happens when x is really, really big? So for big x's, this whole term over here goes to 0. This gets smaller and smaller. I mean, imagine I plug in a billion. 27 over a billion minus 4 is still a billion. This is going to go to 0. This whole term disappears, and the function h of x will approach this line, 2x plus 7. So that will be our asymptote. So that's how we find horizontal or oblique or slant asymptotes, is we do long division and then we ignore the remainder. We just take the equation of the line we get on top. And since the degree of the top is one more than the degree of the bottom, we're always going to get a line here. Okay, so then my slant asymptote will be the line y equals 2x plus 7. Okay, so let's put together what we have so far. We'll start building our graph down here. So I had a vertical asymptote at x equals 4. And I'll write that on here, x equals 4. We have a slant asymptote, y equals 2x plus 7. So that is a y-intercept at 0, 7, 4, 5, 6, 7. And then a slope of 2. So if I go over 1 up 2, I get something that looks like this. And I'm going to dash this in because this is an asymptote. The graph is just going to get closer and closer. Now, remember, technically, with at least with horizontal asymptotes, you can cross over a horizontal asymptote in the middle. With these, we're never going to cross over these slant asymptotes. Now, I want you to look at this picture here. I want you to see that we've got 4 kind of quadrants, that these 2 lines break everything up into 4 quadrants. My graph is going to live in 2 of those quadrants. So my graph maybe will live here. Let me do this in a different color. So maybe we'll have a graph that looks like this blue graph here. Maybe it lives here in this corner up here, hugging both of these asymptotes. And maybe the other half of the graph will live here. Notice I'm not crossing over either asymptote. Or maybe the graph comes in here, tries to go through that little intersection there, but it can't because it can't cross anything, so it has to turn around. And then something like that up here. Now, it can't do this. This would be impossible. The graph could not live here and here. That would fail the vertical line test. Could the graph, do we have more colors? Yeah. Could the graph possibly live here and here? Possible. Usually these will be diagonal across from each other, but there's nothing that says it can't look like this. Or maybe these 2 sections up here. So we've got these 2 dashed lines, and we're going to have 2 sections, but we'll never have 2 on top of each other because that would fail the vertical line test. So really what we're going to do now is just plot a bunch of points until we figure out which 2 sections we live in. And the easiest points to plot are intercepts. So let's find our intercepts. So the x-intercept, remember the only way to find x-intercepts, you always set the function equal to 0 and solve. You set y equal to 0. The only way a fraction equals 0 is if the top equals 0. So we're going to set the top equal to 0. It's a good thing we've already factored that. So we get 2x minus 1 times x plus 1 equals 0. So we get 2 x-intercepts. One will be at 1/2 and one at -1. And then, of course, intercepts are points, not numbers. So we got to write these as points. Let's put those on our graph. 1/2, 0, and -1, 0. So that's right there. Okay. Now we got to figure out this line here was y equals 2x plus 7. Let's write that along the line. So where's this line intersecting the x-axis? Where does y equal 0? So I don't need to write all this. I'm not going to put it on the graph. I'm just doing this and then I'm going to erase it. I just want to see this other x-intercept I found, -1, 0. I need to check, is it here in this region or is it on the other side? It's going to be here. So I want to find the y or the x-intercept of that line there. So if we set that guy equal to 0, we'll get x equals -7/2. So that's like -3.5 there. That's our asymptote. That's not part of our graph. And of course, that solid dot there is not part of our graph either. That was just for that asymptote. Okay, so -1 will live here somewhere. So that tells me that this graph is going to come in, cross over, and then hug this asymptote here. Remember, long-term end behavior, the graph either has to come backwards like this or like this and hug this asymptote. Over here, the graph either needs to come down or go up and hug that asymptote. We just got to figure out which one. Okay, let's find our y-intercept. How do we always find y-intercepts? By plugging in x equals 0. We want h of 0. So we're in expanded form here. We can just, it's going to be the constants here because all the x's are 0. So that's going to be the 0.014. Check that on your own. So that will be a point way in here, 0.014. Now remember, this graph's not going to cross over our asymptote. So now we know this chunk of the graph has to live like this. It's got to hit those points we just found. Let's really blue those in and hug those two asymptotes. Now, our graph can't also live up here. This would be impossible because that would fail the vertical line test. So now we got to figure out, does the other half of the graph live right here in this little corner, hugging these asymptotes, or does it live up here in this little corner? Now, even if it lives up here, remember, it can't do this. It can't come backwards and come like that. That fails the vertical line test. I see students do that all the time. If it does live up here in this region, it's got to always be going to the right. So it might come and go something like that. Remember, here's our asymptote. So it's never coming back on itself. And I think this is what we're going to get. Now, how do we see that? We plot some more points. So I need to plot a point over in this region, any place over here past x equals 4, and I need to see, is my y value above this line or below the line? Do I get something bigger than what I get here or not? So let's pick an x value over here. So let's pick an x in the region 4 to infinity. And we'll pick 5. Why 5? Because it's a nice, pretty number. All right, h of 5. So we're going to plug in the original. We can probably do this in our head. What do we get there? 25, so 55, 54 over 1. So we get 54. So that means I know the point 554 is on the graph. Now my question is that above this line or below the line? Well, what would I get on the line at 5? Here's 5. What's this spot right there? Well, I would just plug 5 in here. So what do I get? 10, I get 17. So that's 517. I'm way above that. So we're way up here, and we're just going to kind of pick a spot there. There's the point 554. That means my graph has to live up in this corner here. And it's going to hug both of those asymptotes. It's riding up along this asymptote, coming down, not going back. It can't go back on itself. It cannot do something like this That would fail the vertical line test. It's coming down from infinity and then making a turn and writing up this asymptote. And let's actually graph this. Okay, so here's our graph. It looks like this. Oh, no, it doesn't. That should be a minus, plus. This is plus. And minus 1. Okay, my y-intercept was wrong there, so I knew it had to be wrong. See our y-intercept right there. Add a quarter. There are the x-intercepts. Now, this Desmos here is not going to put in the asymptotes. Let's add the asymptotes on top of this. So x equals 4. There's our vertical asymptote. And then what did we have? Y equals 2x plus 7. There is our slant, also known as an oblique asymptote. And see how the graph is getting closer and closer to the asymptotes and lives in between them in this particular case. And that's a good place to stop.